Okay. Hey guys, I messed up my recording last time, so I'm just going to upload this in order to have a full recording. But hopefully you can see my screen. We're just going to be doing an application of machining practices. So it's just a huge review of of stuff that we've been talking about the past few weeks, and I hope that you guys learn something. So what we're going to be doing is we're going to be taking this 30-pound part from BattleBots, and we're going to be going through the entire process of how we're going to machine it. So just as a review of week 5, we've got a few machines that we can work with. First is the mill, which we can do several different operations with. We've got the lathe, which is special for parts that are cylindrically symmetrical. And then the water jet, which is important for cutting two-dimensional profiles. With drawings, I want you guys to remember that drawings are used for holding dimensions and different views so that when we go into the shop, we can just bring a simple sheet of paper instead of having to remember things or trying to bring in like a computer. Paper is always easier. And then you can mark it up if you need to change anything. For tooling, there are so many different kinds of tools that you can use. Just because we are limited by the number of machines doesn't mean we're limited by the number of tools we can use in those machines. And so I won't go over all of them, but we're going to cover quite a few today. And then operations. There are a ton of operations we can do, especially with the mill. And we're going to be going over a few of those today as well. So safety, first, we want to talk about safety. If you've taken any kind of course in an engineering shop before, you probably already know this kind of stuff, but it's always worth covering. So as always, wear eye protection. We have plenty of pairs of safety glasses in the CMA, but if you want to eventually buy your own, it's not a bad idea. You can use them for years. Closed-toed shoes. You don't want to wear flip-flops or maybe even Crocs into the machine shop. It's just not a good idea. Long pants. You don't have to have long pants. It doesn't hurt, especially now that it's getting colder. For sleeves, if you're wearing long sleeves, though, you have to roll them up. And same idea is you want to tie your long hair back. So you don't want to risk anything getting caught into your machines. Gloves on only when appropriate. And so again, the same idea where you don't want anything caught in the machines. I would say that the only time you want to be wearing gloves is if you're welding. If you get the chance to learn how to weld, I'd encourage you to do it. It's something that not a lot of people in RoboJackets know how to do. And it's a really important skill that you can use in a lot of different situations. No horseplay. That's pretty self-explanatory. And then in the CMA, we're only going to be working with metal. We aren't going to be machining wood at all. So if you look at this picture, you'll notice this guy is actually violating a few different safety things. For one, he's wearing long sleeves and gloves, which on this drill press probably isn't a good idea. He's also not wearing safety glasses, which you might be able to not tell because of the watermark, but he's using his OSHA-approved safety squint. And another thing that's worth mentioning is he isn't actually working at his part that he's operating on. He's clearly has his hand on the lever, but he's looking at the camera instead of looking at what he's doing, which is pretty dangerous. He's also not holding his part. So as kind of a safety thing in the CMA, we've got what's called the SUMS console. So when you go into the machine shop, you'll be able to see the screen, and when you log in with your Buzz card, then you'll be able to see the screen that pops up. And as you get trained on different machines, these green login buttons will appear. And what you have to do is when you go into the shop, you have to go in with a buddy, and you have to both sign in. And if you only have one person or no people actually signed in, the machine won't actually start up. You have to be fully logged in with a buddy in order to use the machine. And so it's just an extra step of safety. So now we're going to look at this part. It's worth noting it's made out of aluminum. So there are several different operations that need to be conducted on this part. So for example, the most obvious one is all these holes. We have a lot of holes. We also have this pocket here. We have some facing operations where you can see that there's a little offset between the face height of this part, and this part. And we've also got some holes on the side. And you can't tell, but these holes on the sides are actually tapped. So we have to worry about the threads as well. So let's start. We're going to assume that your mech lead hands you this drawing and says, hey, make this. So naturally, you're going to make it. And how are we going to start? Well, if you think about, like, if someone asks you to make a sandwich, and you're like, oh, okay, well, start spreading the peanut butter on the sandwich. Well, no, hold on. You got to get the ingredients first. We got to pick out the stock. So we walk over to the stock area and we find some good aluminum. Well, what do we need to consider? What do we call good aluminum? Well, first it has to be the right kind of aluminum. If you want 6061, then that's what you want to pick. We also want to consider if we have the right size. If if you pick out a piece of stock, it's 9 times out of 10, it's not going to be totally clean, just a solid block. It's going to have plenty of cuts that other people have made into it. So you want to actually make sure that you have enough space for what you're going to be building. You also want to consider the thickness. If you have too thin or too thick of a part, that's no good. So you want to pick exactly what you need. So once you have the stock chosen, you have to figure out, what order are you going to take? There are a lot of different operations. What's the best way to do it? And of course, there are multiple orders to start the part, but there's always a better option. So what are we going to start with? We're going to start with water jetting. So first things first, we're going to cut the profile of the drawing, or of this part. And so what do I mean by that? Well, we're going to stick this, just the profile. So these holes, all these big holes, and then the outer lines. And so if you imagine this part without these internal face lines, then that's what our water jet is going to output. So it's going to be completely flat, but it'll have all these holes in it. So now what's next? Over to the mill. And we're going to start facing things. So an important first step with any part is if stock is oversized. So I've mentioned a couple of weeks ago, but stock isn't going to be the exact size that it says it is. So like if it's 1/4 inch, it's probably not going to be exactly 1/4 inch. And if it's a little too thick, sometimes that might not work for your measurements. So you might want to face the entire part in order to get it to a proper 1/4 inch. We also have some facing operations with this piece. So I mentioned this before. So what kind of tools are we going to need to use in order to complete all this facing? And that's something we're gonna mention later, but we're going to be using end mills and facing end mills. And what are different ways that we can use? I could have sworn I had a slide on this. Hold on. Okay, yeah, it'll be later. So yeah, we need to think about how we're going to hold this piece. We're not going to hold it by hands. That wouldn't really work that well. And so also, how should our piece be oriented? And if you're familiar with the mill, you know that the mill tool comes straight down from the top. So we want our piece to be oriented so that the faced parts are on top. So to hold our tool, or to hold our piece, we're going to be using vices. And just because we have only a vice doesn't mean we can use that. If you think about the part that we have, if it's sitting on the bottom of the vice, there are a couple issues. One is if we want to face the entire thing, the sides of this vice are going to get in the way. And if we ever have an operation where you want to drill straight down, then the bottom of the vice is going to get in the way. So that's why we use something called parallels. So these are just rectangular pieces of metal that we can stick into this vice so that we have our piece kind of sitting on top so that the vice won't get in the way of the tool. Another thing is if the part is too large to use just the vice, we can use finger clamps and step blocks. So unfortunately, I don't have a picture of these in use, but if you learn how to use the mill, then you'll probably get shown how to use them. So to think about it, we're also going to be using tools to use the facing operations. So I mentioned we're going to be using facing end mills specifically. And you also have to think about what order you want to do it. So if you're looking at this large facing end mill, it's 2 to 4 inches in diameter. you want to use this in order to do a bulk of your facing. If you use just a 1/4 inch end mill, it's going to take a long time. It's like if you're using a lawnmower on a big lawn of grass, do you want to use the small push one, or do you want to use like a big industrial lawnmower? And the answer is you want to use a big industrial lawnmower, except for like the corners near the house or like around trees, you'd probably use a smaller one to clean it up. And so there are other things we have to think about besides just the diameter of the tool. We have to think about length. Is it long enough to work through our entire part? Are we working with a super thick piece of metal that this might not be enough? Or do we have enough on the back ends that the mill can properly hold onto it? We have to think about flute number. We're working with aluminum, so we want to use about 2 flutes. If we were working with steel, we'd probably want to use 4 or more. And the material. We use different coatings on our end mills, but we want to make sure we use the proper material and coating so that if we're working with aluminum, it's not going to interfere with it at all. And even though you've just picked your tool, you've still got more things to think about. You also have to think about spindle speed and tool feed. And these are important because, again, since we're working with aluminum, the spindle speed matters a lot. And then tool feed matters. If you try to go too fast or too slow, things can go wrong and you might break apart and you might put yourself in danger. So you have to think about it really carefully. And so a good tool is this link here. Let me go ahead and click it and run the web app. But this is a super useful website, and you can just plug in all sorts of information into it, and it's going to spit out a number of how fast you're supposed to go or how fast it's supposed to speed or spin. So you can check up here, and you can change whatever you want. And I encourage you to bookmark this website for future reference. So now we've got this piece faced, we've got the profile cut out, we've got all the holes done, except there's an issue, is the water jet doesn't create perfect holes. It creates perfect holes on top when it starts cutting, but as the pressure decreases because it's working through this metal, the bottom of the holes is going to be slightly smaller. And it's called taper. So we have to clear them out somehow. And so we're still at the mill. And we could use a drill press, we could use a hand drill, but we're at the mill, so we might as well use the mill. And if you think about what order we're going to do the holes, we're going to want to start with the small ones because the big hole is going to have a purpose, and we'll talk about that later. So now that we're working with the drilling operations and no longer facing, we're going to be using different tools. We're going to be using drill bits, and so they're different from because they're meant for drilling. And again, we've got a handy dandy little website for determining what drill bit size we're going to use. And again, I'd recommend that you bookmark this website. You can just rewind until I go over this, and then you can just pause and copy down that link. But it's very useful, and we want to make sure we're using the correct drill bit for what we're doing. And something important to notice is it has different clearances, so it depends on what kind of fit you want to choose the right bit. And so spindle speeds, same idea. You don't want to have the same spindle speed for steel as you do for aluminum. Generally, the rule of thumb is 1200 is good aluminum speed, but aluminum is going to be significantly faster than it is for steel. So for this part, because it's aluminum, we'll just start with 1200. If it doesn't work, then we can play around with the speed, but 1200 is a good starting point. So the large hole, like I said, it's a little different because it's not for screws or bolts. It's used for this ball bearing. And generally with ball bearings, we want a nice close press fit. And so again, we're going to go to that website. We're going to find the correct bit for the press fit, and we're going to choose the proper tool for the job. So how do you go about properly making a press fit? This isn't something that you can just, throw down the drill bit and pull it out and you're good. Sometimes you have to make sure that your tolerancing is correct. So what you'd want to do is you'd want to put in the smallest possible tolerance of drill size. So you drill out that hole, and then you take your bearing, and without taking the part out of the machine or changing any dimensions so you don't mess up your zero, you just try to press in that bearing into the hole. And if it doesn't fit properly, then you just go one size up. Try it again, try the bearing again, and if it has a close press fit, then you're good. What we want to avoid is creating too large of a hole, and then we'd have to start over because we can't just fill in a hole. That would be no good. And so always take your time with these kinds of things because it takes less time to go through a bunch of drilling operations than it would to completely start over. So now I've got a few more holes to drill. And so I'm going to go back to the drawing here. So you'll notice we did the ones on this front face, but now I have to do the ones on the sides here. And so you can see the hidden lines here showing the profile if you had X-ray vision. And something you'll notice is that the hole callouts for this front face, they say through, which means it goes all the way through the part. But this other one, this symbol means depth. So it has a particular depth. So if you look at this, it has a depth of 0.38. And you'll see that in this outline, it doesn't go all the way through, which means we do have to be careful about how deep we're going. But something else to consider is that we're starting these holes from scratch. So again, we're going to have to worry about workpiece holding. And again, we're going to use a vise with parallel grips. It's a really good go-to. However, if the workpiece happens to extend too much upwards, you can create what's called a jig, which is just anything that a person would construct in order to make a machine do what the person needs it to do, but it isn't necessarily built for. So if you have a need where you think the mill isn't going to do what you want it to, but you think it could if you added a certain attachment, talk to someone like a senior member about if you can do it a better way, or if they can help create what you need in order to make your part. So the types of tools that we need to make these drilling operations. We don't need just these drill bits, we need a sensor drill bit. What a sensor drill bit does is it allows you to cut out small pilot holes, because drill bits can't necessarily cut with the center. So like if you're trying to make a hole from scratch, drill bits can't always do it. You'd want to start with a center drill bit in order to most effectively make the part. Plus, center drill bits help make sure that if you end up drilling by hands later, you don't have any drift when you start. It'll be positioned in the proper place. And again, with spindle speeds, you're going to be having the same rule of thumb. So aluminum is going to be faster than steel. So now that we have all these holes drilled and cleared, some need to be threaded. As I mentioned, those ones that we just drilled, these need to be threaded. So we're still in the mill. You could do this by hand, but we want to go use these tapping tools. So these labels denote the size, so it'd be diameter and thread size. And you can tell because of the fractions and how they're set up that it's a imperial unit. And so when it comes to, you're looking at all these different apps and you're wondering, okay, which one do I use? Because these aren't all the same. So assuming these are the correct sizes for what we want to do, we'd want to start with this, this tap first. The reason is you can see that these grooves fully develop pretty late. And what that means is when you're starting a tap, it's a gradual process in order to cut into the material. And this is super effective. All it means is that the threads at the bottom, because this would be upside down when you're threading, these threads here wouldn't be fully developed. And so what you'd have to do is you'd tap with this first, then you would go to something like this where it gets to full thread faster, and then you get to something like this last one where it starts threading almost immediately. And this is the most effective way to tap out a thread. It has the least chance of breaking a tap, which happens all the time, but we would try to avoid. and then you can use it pretty effectively. So now you're done. Well, kind of, not exactly. There are still a few things that you might have to do in order to finish your part. For example, when you drill out holes, sometimes you'll end up with kind of jagged edges near near that hole, or just on the sides of your part. And so you'll need to deburr them with a sander or deburring tool. Then if any features didn't come out quite right, you might have to remachine them a little bit. Again, it's better to just try to redo some stuff or to work slowly and make sure everything's right rather than having to start over. And then if you have puzzle fits or anything that has to be really closely done, you can just file it by hand until it works. But otherwise, that's your part. It was several different iterations through different machines, but that was a real part that had to be made. So I'm not gonna do the Kahoot with you guys. Unfortunately, it was just a review of past weeks, so you've already done this question before. There's only one really new question that I want to kind of point out, and it's what kind of material is magnetic? And so this is an important note. If you have a piece of stock and you're not sure if it's steel or aluminum, the easiest way to tell, besides like if you could figure out weight by hand, would be to use a magnet. So steel is magnetic and aluminum is not. And so if you throw a magnet at the steel or at the stock and it sticks, then it would be steel. And if it falls off, then either you threw it wrong or it's aluminum. And then the guide. I'm just going to run through the guide real fast because it's a little different. Instead of doing just a CAD guide where I'm going through each step with you, you're going to be doing your own thing. So what I want you to do is I want you to take any object in your room that you own, and preferably it has something with more complex features than just like a phone or a water bottle. Something that would take some effort to model. And then just take any kind of measuring tool. Hopefully you have a ruler or some kind of measuring device. If you really want to use a protractor for angles, go for it. What you're going to do is you're going to CAD the part as accurately as you can in Inventor. If it has multiple parts, I'd encourage you to try turning it into an assembly to get some extra practice in. And then when you're done, I want you to take a picture, a screenshot, or a render. I'm going to talk about renders later. And just email it to me with this formatting just so I know who it's from and what it is. And if you want to get fancy, I'm going to show you, I'm going to lead you through these slides real fast. But yeah, you don't have to do this. If you don't want to, that's okay. But if you want to show off, I'm really excited to see what you guys make. So render in Inventor. Sometimes simple screenshots aren't enough. You want to use some fancy material in your project, and you want to show it off, whether it's in like a portfolio for your resume, or if you want to just have a fancy picture for your design review. Renders are cool. And so we're going to use the Environments tab to get to our Inventor Studio. And so Inventor Studio is used for renders, and it's used for animations. I'll talk about animations later. We're going to be dealing with renders. So you're going to use the top left button. It's going to say Render Image, and you're just going to populate with the settings that I've described. And again, here, under the Renderer tab, you can do it a few different ways. You can go by time or iteration. And what that means is once you hit start, it's going to render until it meets this stopping term, and then it's done. So you can like hit start, walk away, come back, and it'll be done. Or you can click until satisfactory, where you'll watch the rendering process happen in real time. So you're going to see it as it gets clearer and clearer. And so you just have to sit and watch until it's done, or be okay with the processing power that it would take if you walked away for like an hour. And so you'll see what actually happens here. You can see like this is kind of staticky or grainy. And this is when I initially started rendering. And then after like 30 seconds, it ended up looking like this. And so if you had a more complex material, then it would take longer, naturally. But it kind of adds some shadows, adds some different lighting, and it makes it look much better. And so to save it, just follow the instructions in the slide, and then you can finish. And so as I mentioned before, you can create animations in Inventor Studio. Again, it's something you can use for your portfolio, or if you want to show something during a design review and you just want to have it pre-prepared, you can create an animation. I haven't made anything for it, but if you really want to learn how, and you want to learn it from me instead of like trying to look it up, let me know, and I'll think about making it probably in the spring. But yeah, that's it. That is the end of mechanical training. I'm glad you guys stuck with it. I'm glad you guys are watching this. I hope you learned something. And if you did, or if you didn't, let me know in a poll. The poll is in the email that I've been sending out. Also, probably link it in the description below. But I'm glad you guys came, and I hope to see what you guys can do in RoboJackets.